All right, this is looking at inductors and circuits. So again, an inductor, it's like a solenoid or a toroid. And two things about inductors that are important for circuits. Number one, they store energy in their magnetic field. And then number two, they prevent changes in current. It's something called impedance. They resist changes in current, not current. Resistors resist current. So if you have a circuit and there's no current, the inductor is going to try to prevent current from building up. So if there's no inductor in a circuit, and I'm trying to have battery leave the current, the battery's just going to leave the current automatically, just go mer. If I have an inductor there, it's going to build up slowly. So if I have an inductor and I connect power, the circuit's going to go mer, 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 and eventually reach steady state. It's not going to happen instantly. Likewise, if you have an inductor and you cut off power, it's going to prevent power from cutting off instantaneously. It'll have to cut off over time, slowly. So this is inductors, and let's go ahead and look at inductors. Here's a look at the charging circuit. So I have battery, resistor, and an inductor. The circuit's called an LR circuit because I have an inductor L and a resistor R. So when I connect power, you're not going to see current immediately jump to its steady state. It's going to start slowly, and then over time, a couple of seconds, build to its steady state. Here's the math for the charging circuit. Now, if you've been paying attention in Physics C this year, you know the math behind this. This is a differential equation, and it's the one we've been doing all year. So the switch is initially open. At time t equals 0, the switch is going to close, allowing the circuit to charge. So if there was no inductor, the current would just immediately jump to epsilon over R, the battery voltage over R. That's from Ohm's law. Instead, it's going to build there over time. So the voltage across the resistor, because V equals IR, since the current's going to build, the voltage across the resistor, which is I times R, is going to start at 0, because there's no current, and then build over time to the battery voltage, because after a while, the inductor here will just behave as a wire. The voltage across the inductor, so this is a bit more complicated. If you have initially all the battery EMF going this way, the inductor is going to send it an equal but opposite EMF to start off. Now, over time, the rate of change of current is going to decrease. So di dt is going to decrease. So the back EMF is going to decrease. Because over time, instead of having a back EMF, you'll have EMF stored in the inductor in a magnetic field. And then the current, I of t, as stated before, that's going to build over time to be battery voltage over R. And we're going to get an equation for that time, I of t, and we're going to do that using Kirchhoff's loop law. So here's Kirchhoff's loop law, or Kirchhoff's voltage law, applied to this circuit. So the battery is going to supply voltage. Then you're going to have voltage kind of being dropped in two different forms. Heat in the resistor, so that's voltage dissipated in the resistor, and then back EMF in the inductor. And that's going to happen over time. Of course, initially, VR is 0, VL is epsilon. And let's re-express these terms in terms of things that are useful. So we have battery EMF minus the voltage across the resistor, which is IR, and then the voltage in an inductor is di dt. And now here we are. We have di dt in the same equation as I. So the current depends on the rate of change of current, which makes this a first order differential equation. And we're going to solve it. Now, this is not difficult because it's just going to be the same first order equation we've been solving all year. All right, so I'm trying to get it in a form such that I can separate the variables. In order to separate the variables and to make the integration easier, I divided both sides by negative r. And now I have I minus epsilon over r equals negative L over I di dt. Now my next step is just to separate the variables. I'm going to take all of this and divide it under di, move everything else to the other side and get separate variables here. So I separate the variables, and that's what I have. So di over I minus epsilon over r equals negative r over L dt. Now I have to get bounds. So the current starts at 0. So on the left, I'm integrating the current. That starts at 0, and it goes to some variable current. And then time always starts at 0. So those are the bounds. Current from 0 to I of t, time from 0 to t, as it always is. Now I integrate both sides. Because I wrote it in this form, and this is an I, not a 1, it says a 1, I think. I don't really have to use U substitution. Well, I would, but the left side is just going to be ln of I minus epsilon over R, and the right side is just negative R over L times T. Okay, so I integrated both sides, and that's what I got. Now I just plug in my bounds. All right, so that's what you get when you plug in bounds. On the left, the right side is just going to stay negative R over L times T. And now I'm going to use properties of logs. So this is what I get using properties of logs. Now I raise both sides to the e power. And that's what I get there. And now this can be simplified to I of t equals its steady state value. So its steady state value is epsilon over R, 1 minus e to the negative R over LT. So that's the equation. You should recognize this type of function. This is an asymptotic increase. So the current's going to start at 0, then build to its steady state value asymptotically. So that's the function that we just got from integration. This is how you're going to see it written in a textbook usually. 1 minus e to the negative t over tau. And tau, that's your time constant. The bigger the time constant is, the more time it takes to reach a steady state, and vice versa. So it's the time constant. For an LR circuit, not surprisingly, the time constant is L over R. And then to get the voltage function for the resistor, V equals IR, Ohm's law. And then the inductor is just opposite the resistor. So when you have an LR circuit and it's just one resistor, one inductor, whatever the voltage in the resistor is, the inductor is just the opposite of that compared to the battery. And then, so here's all three functions. So the current starts at 0 and builds to its steady state asymptotically. That's what that function says. The resistor does the same thing. It starts off, it gets no volts originally. Then it starts getting the battery voltage over time. Once the inductor no longer has back EMF, it's not taking any volts away from the resistor is going to get the full battery voltage after a long time. And then the inductor, as the rate of change of current, because as the current increases, you see here, as the current increases, di dt is decreasing. So di dt is going to decrease. So that means the flux, the rate of change of flux is decreasing. Eventually there's no change in flux, so there'll be no back EMF, and this will drop to 0. But when that happens, the inductor does have those volts stored in its magnetic field at steady state. Now on to the discharging circuit. So in this case, we have a battery, and we have two switches that are initially both open. And now we have, again, up here, an inductor and a resistor that are in series. So I'm going to close S1, and what that's going to do is fully charge the inductor. So we're going to have the charging circuit that we just had. It's going to charge, it's going to reach a steady state. Now, switch 1's going to open, and switch 2 is going to close. And what switch 1 opening does, it cuts off the battery. So before, at steady state with switch 1 closed, the inductor stored up a bunch of energy. So it has energy stored up. And when switch 1 was closed, there was current kind of going this way through the inductor. So there was current through the inductor to the left. And when you cut off the battery, that current's going to try to stop because the battery is no longer there. So the inductor is going to keep current going because the inductor resists changes in current, so it's going to keep current going. So for a little bit, it's going to act like a battery through this new circuit here. Okay, so the inductor acts as a battery, and we can find out the current again through the circuit. So there's a current that's going to be initially epsilon over R. So that's what the current was. It's going to stay that way, but now it's going to decrease, and we're going to solve for what it is. Again, we're going to start with Kirchhoff's loop law. So these two voltages, the resistor and the inductor, add up to 0 because we're using the loop law. You go around a complete loop in a circuit, you get a voltage sum of 0. And now we plug in negative IR for the voltage in the resistor. It's negative because resistors always drop voltage. And then the formula for voltage across an inductor was negative L di dt. So we have that. Now we have to go through and again do the whole differential equation. Separate the variables. plug in bounds, and then solve. So I'm going to get them on separate sides, the voltage for the resistor and the voltage for the capacitor. And I'm going to solve for I this way. The reason why I want to separate I is I want to get the variables separate. So I'm going to get di and I on the same side, and then all the constants, which are L and R, on the same side with dt. And there we go. The variables are now separate, and now we just have to plug in our bounds. So the initial current, it wasn't like the charging circuit where the initial current was 0. Here it's epsilon over R, because that's what it was. We had a fully functioning circuit going around with a steady state current of epsilon over R. So that's where we're going to start off. Now it's going to decrease, but it started off as epsilon over R, and it's going to go to some current. We're just going to call it I of t. And again, time always goes from 0 to t. Now this is a pretty simple equation to solve. Again, di over I, it's ln of I. So ln of I, plug in the bounds on both sides. And then you just get the bounds plugged in, ln of I of t minus ln of epsilon over R. Properties of logs again. Now you raise e to both sides. And it basically gives us the answer. So the answer is I of t. It's epsilon over R, e to negative R over LT. Now what that means mathematically is the current starts off at epsilon over R, which was the current before the switches were flipped. And then e to negative R over LT, that's just an asymptotic decreasing function. So it starts off at what the current was and then decreases asymptotically. Here's all the functions for the discharging circuit. So we have the current, which we just got. Using Ohm's law, again, V equals IR, you get the voltage across the resistor, which is just going to be whatever it was in the inductor. So the inductor is the battery for the resistor, so it'll have equal voltages at different times. And those are all your functions. They are all asymptotically decreasing because this is a discharging circuit. And going to the graphs, again, the current starts at what it was at steady state with the circuit running with the battery, decreases to 0 asymptotically. The voltage across the resistor decreases asymptotically. The inductor does the same thing, decreases asymptotically. Everything in a discharging circuit decreases asymptotically. And again, contrast that to if there was no inductor. If there was no inductor, the current would just go immediately to 0 the second the switches were flipped. Example A gives a circuit, basically a simple charging circuit. There's two switches, S1 and S2. We never actually use S2 here. S1 is just closed, and we're looking at the charging circuit and some questions about the charging circuit. So part A, what is the current through the resistor when switch 1 is closed? Well, it's just looking at what an inductor does. There's no current because there's no circuit right now. You have an open circuit, so there's no current flowing. And since there's an inductor there, the current can't immediately jump to anything, so it's going to stay 0. It'll increase over time, but right when the switch is closed, it's 0. And there's the answer, it's 0, and that is because current cannot instantaneously change in an inductor. Remember, that's probably the most important thing to remember about inductors. Inductors make it so current can't instantaneously change. Part B, what is the voltage across the inductor just after the switch is closed? Well, there was no current. The reason why there was no current is because the battery is going to give a certain EMF this way. There's no current because the inductor gives an equal and opposite back EMF. And that back EMF will decrease over time, and there will eventually be current, but initially there is no current because the back EMF exactly cancels out the battery. And that's the answer to this one. So it's equal to epsilon, the EMF of the battery. Part C, find the potential across the inductor as a function of time. We're not going to go ahead and derive this again. We look at the derivation. So we'll use what we got, which is that for the inductor, it starts off with the battery voltage, then decreases asymptotically by negative t over tau, where tau is the time constant, which for an LR circuit, the time constant is L over R. So the time constant, L over R, 4 over 20, it's 0.2. And the units for the time constant are henries over ohms. There's plugging in numbers, and that is the final answer. Part D, at what rate is the energy stored in the inductor increasing at time of 2 seconds? Well, the rate of energy in physics, that's called power, so we're solving for power here. Okay, so power again is the rate of change of energy. So it's the derivative of the energy stored, which is U. So it's du dt. And the energy stored in an inductor is 1/2 Li squared. And the derivative of 1/2 Li squared is 2 times 1/2, so it's 1 times Li. And when we took the derivative, we have di dt in there. So we have to actually find di dt. So the function for current is the current function for a charging LR circuit, which is steady state current, which is battery EMF over the resistance, times 1 minus e to the negative R over LT. So that's I of t. And again, we want to find the IDT, so we just take the derivative of that, which is an easy derivative. Hopefully any physics T student knows how to do the derivative of e to the negative 5t. So there you go, di dt is 25 e to the negative 5t. Now we go back to the original function. So we're going to plug this in to di dt at t equals 2. Likewise, for the current function I of t, we plug this in for I, again at t equals 2. And then L is 4 henries. So there we go, 4 henries times I of t at 2 times di dt at 2. And you get a final answer of 0.02 watts. Example B is a discharging circuit. So this inductor right here was fully charged. It had 100 amps going through it when the battery was cut off, and it's going to discharge to the 1 ohm resistor here. Here's a simulation of example B. So the inductor has an initial current, so I'm going to go ahead and give it an initial current. And when I connect power, to kind of look at how inductors work, all the current's initially through the resistor, and the inductor will build up current over time. Now, after a little bit of time, you're going to see that the branch with the resistor, that current's going to die out because an inductor, once it reaches steady state, basically acts like a wire with no resistance. So an inductor kind of starts off as a short circuit. Current doesn't flow through it, but after a while, you see right here, it acts as a wire with no resistance. Now example B looks at when you just have the circuit of the inductor and the resistor without the battery. So this is the circuit that we're going to look at in example B. So when I cut off power, there was still an initial current because the inductor resisted the stop in the current. The actual math involved in example B is pretty straightforward. I of t is I sub 0, which is 10, e to the negative r over L times t. And then the voltage drop across the resistor is just, using Ohm's law, IR. Just multiply that by IR. Then you just plug numbers into this formula here. So the current starts off initially as 100. Resistance is 1. So that's the initial voltage of 100 volts across the resistor. And then it drops over time. Okay. Part B, find the time needed for the current to reach 10 amps. Well, again, the current function is initial current, which is 100, e to the negative r over L times t. So plug in numbers, and then solve for t. So I of t is 10. Here's just some math. Divide both sides by 100. Then do ln of both sides, and then solve for t. So t is ln of 0.1 over 0.2, and you get 11.5 seconds as the final answer for part B. Example C, the circuit on the right is allowed to reach a steady state. So the switch is initially open, and the circuit right here is allowed to reach a steady state. And then at time t equals 0, the switch is going to close. Here's example C on a simulation. So the switch is open. The circuit is the battery and the 2 resistors. When I go ahead and close the switch, current will go through the inductor slowly. And then after a while, all the current goes through the inductor. So remember, an inductor starts off as basically a short circuit as it's having the back EMF and building up charge. But once the inductor is fully charged and there's no more back EMF, it's going to act like a wire with no resistance. So at this junction, current can go through the inductor or through the resistor. It's all going to go through the inductor because the inductor has no resistance. So part A on this question says, what's the potential across the inductor? Well, this is not the same as the circuits we were looking at earlier where the inductor is going to get all the back EMF of the battery. So here, there's going to be a back EMF in the inductor, but it's not going to be the full 120 volts of the battery. And that's because it's in parallel with the 40 ohm resistor. So it's only going to get the voltage of that resistor. So you're going to have a certain number of volts when this voltage goes around the circuit. That's going to be dropped in either the 40 ohm resistor or the 20 ohm resistor. And it's going to be proportional based on their resistances. So not all of it's going to be in the inductor because the inductor is in parallel with this resistor right here. So you have 80 volts going to the inductor as back EMF. And that's because you have this circuit originally. And in series, voltage is split proportionally. So you have 40 volts being dropped by the 20 ohm resistor and 80 ohms being dropped by the 40 ohm resistor. So those 40 volts, when you close the switch, it's going to have 40 volts going this way that the inductor is going to kind of spit back in the form of back EMF. Part B, at what rate is the current increasing the inductor at time t equals 0? So we know that the back EMF in an inductor is negative L di dt. So at what rate is the current increasing? So this is asking for di dt. So we just solve for di dt. It's EMF over L. So the EMF across the inductor is 80 over the inductance, which is 2.5. And you get that the current is increasing at a rate of 32 amperes per second. Part C, how much current flows through the inductor after the switch has been closed for a long time? So when you close the switch, this is important, when you have an inductor in a circuit and it's reached a steady state, so a long time means steady state, the inductor is basically going to behave as a wire with no resistance. So after a long time, your circuit is going to look like this. It's going to go here, completely skipping the 40 ohm resistor. Because the 40 ohm resistor has resistance, the inductor has no resistance, all the current's going to go to the inductor. So inductors at steady state behave as a wire. So no current's going to go to the 40 ohm resistor. So the answer is going to be basically, well, look at the circuit. You have only 20 total ohms of resistance. So the answer is 120 over 20. So the answer is 6 amps for the current to the inductor. All right, so that is inductors in circuits. Again, the most important thing to remember about inductors in general is that they prevent instantaneous change in current. So they have something called impedance, which is resistance to change. And then also inductors do act as sort of temporary batteries because they store energy, kind of like capacitors. And next we'll look at what happens when you put an inductor in a circuit with a capacitor. All right, so LC circuits are circuits where you have an inductor, L, and a capacitor, C, in a circuit together. So both inductors and capacitors are going to store energy. An inductor is going to store it in this magnetic field, and a capacitor is going to store energy in an electric field. So they're both able to store energy, and they're both able to discharge. When you put them in a circuit, they can discharge and act as a battery. So let's say I had this fully charged capacitor here, and I let it discharge. It's going to discharge this way with current through the inductor. And once it's fully discharged, the current's going to try to start to die out. But remember, inductors resist instantaneous changes in current. So the inductor's going to keep pushing current through to this plate and fully charge up this plate. And then, of course, after a while, this plate's going to try to discharge. And it's kind of a cycle. So what you have is kind of a game of hot potato between the capacitor and the inductor, where the capacitor's going, here, take this charge. And the inductor's like, no, you take the charge. The capacitor's like, here, take this charge. And the inductor's going, no, you take the charge. And it's a whole cycle. So what you have here is a grown man playing with Pikachu plushies. But you also have periodic motion. So let's go ahead and look at LC circuits. To make an LC circuit, what you basically do is you have a capacitor and an inductor connected to each other. Now first the capacitor is fully charged, and when you have a fully charged capacitor connected to something, it discharges. And eventually the capacitor is going to fully discharge. And when a capacitor fully discharges, the current starts to die down. And what an inductor does, it prevents changes in current. So as the current starts to die down, as the capacitor discharges, the inductor will keep pushing it through to resist the change in current. And that'll push charge to the other plate of the capacitor. And that's how you get the oscillation in. So to look at it step by step, you have one plate of the capacitor discharging. So let's say I had positive charge here, it's going to discharge. So I have current going this way through the inductor until the capacitor is depleted. When the capacitor is depleted, the current's going to try to die, and the inductor will push it through due to its resistance and change in current. That's going to leave positive charge on this plate over here now. And the inductor will no longer have anything going on in it because the inductor now will be out of current. It'll have no more dφ/dt, so it'll no longer be pushing current through. But now, since the capacitor is fully charged, well, now it's going to discharge the other way. And as the capacitor fully discharges, the inductor keeps pushing the current through, and you'll get, again, this plate of the capacitor will be charged after a while. And then it will discharge, and so on and so forth. This is going to be periodic motion that's going to happen here, and it's going to oscillate. So here's the LC circuit in action. I'm going to connect power to it. So this is going to charge the capacitor fully. Now when I disconnect the battery, so the battery is going to be disconnected, there's no power to the circuit, the capacitor discharges. And as current starts to slow down, the inductor pushes it through because it's going to resist changes in current. And because of that, you see it's going to oscillate with the capacitor getting opposite charges on its plate over time. And I'll let it oscillate a couple more times here, and then we'll look at the math behind it. So once the plate fully charges, then the capacitor starts to discharge. And then once the capacitor is not charged anymore, the inductor pushes through the current, allowing the other plate to fully charge. To analyze the LC circuit mathematically, we're going to do Kirchhoff's law because we still have a complete loop. Kirchhoff's voltage law says you go on a whole loop, the sum of the voltages is 0. So there's Kirchhoff's law for this. So the potential difference across the capacitor plate plus the EMF in the inductor equals 0. And we'll express those in terms of other variables. So the voltage across the capacitor is Q, the charge in the capacitor over C, plus L d I dt. And those two equations aren't really compatible as it stands right now. However, current is dq dt, the rate of change of charge. So di dt is just the second derivative. So di dt is the second derivative of charge. We make that substitution, the equation becomes a little bit easier. Okay, I'm going to do one more thing to this equation to make it look like something from mechanics. This is what we have now. Now in mechanics we got an equation for harmonic motion. And this looks very, very similar to it. So I'm going to pull that up now. So this is the equation for harmonic motion from mechanics for springs and pendulums. And the general solution was x of t is x0, the initial condition, cosine omega times t, where omega, that's your angular frequency of the function. So we have a very similar equation here. So instead of x, we have q. And then our omega here, so our omega is going to be the square root of 1 over LC. And if you plug that into the general equation, so the charge in this circuit is q sub 0 cosine angular frequency, which is 1 over the square root of LC, times t. And then relating this to the period, so this is angular frequency, period is angular frequency over 2 pi. So the period of an LC circuit is 2 pi square root of LC. All right, so that's all the math that's going on in an LC circuit. And we'll go ahead and do an example problem on this. Here's an example of an LC circuit. So we have a 12-volt battery charging up a 100 microfarad capacitor. And there's a inductor connected to the capacitor eventually. There's a switch that's going to flip from A to B. So it's at the position shown for a long time, meaning that the capacitor fully charges. So this right here means the capacitor is going to be fully charged. It's going to get 12 volts across it. And then the switch is going to be thrown to position B. And then we're going to have an LC circuit oscillation. So part A says find the maximum charge in the inductor. So the energy considerations for an LC circuit is basically there's a certain amount of energy that's going to be gotten when the capacitor is connected to the battery. So when you connect the capacitor to the battery, it's going to charge up and get some amount of energy on it, which is 1/2 CV squared. That's the energy stored in a capacitor. When you plug in numbers, you get 7.2 times 10 to the negative 3 joules. So it's 7.2 millijoules. And once you have the LC circuit oscillation going on, that energy is going to be shared between the capacitor and the inductor. So the energy in the capacitor plus the energy in the inductor is 7.2 millijoules. And then since the sum is 7.2, at the maximum values, so when all the energy is in the capacitor, which is the maximum energy in the capacitor, then the energy in the inductor is 0. Likewise, when the inductor is at its maximum energy, which is 7.2 millijoules, the capacitor has no energy. So 1/2 Li squared max is equal to 7.2 millijoules. So now we just solve for I. So I is 2 times the maximum energy over L. Now we can plug in numbers. And again, this maximum energy in the inductor is equal to the maximum energy in the capacitor. Those maximum energies obviously occur at different times, but they have the same maximum energy. And plugging in numbers, you get that the maximum current is going to be 0.08 amps. Okay, part B is kind of simple. Calculate the time rate of change of current when the charge in the capacitor is 0.4 millicoulombs. So this is from Kirchhoff's law again, L d I dt, the EMF in the inductor, plus Q over C, the voltage across the capacitor equals 0. So that's solving that for d I dt. Now we plug in numbers and get our final answer of 0.002 amps per second. All right, that was LC circuits, and LC circuits is the last topic in Physics C, so we are done with the curriculum.